general unknown, homework 6, and midterm. I'm just making a list so I don't forget. Let's do some general unknown questions first, because I feel like that's going to be the quickest thing to talk about. And I figure you all want to know about the general unknown as well. So, what do we want to know about the general unknown?
I am confused on this chart.
That chart. Okay, so this chart, let's think about, I know I went through my information on the general unknown very quickly, but essentially what we want to start doing is we want to think about all of the chemical tests we did over the last 8 weeks, and we want to think about 2 things. We want to think about a broad test versus a specific test. Now, a specific test would be like the sodium test, right? So if you were doing, you could get your unknown, dissolve it in water, and instantly go and say, I'm going to do the sodium test first. It's a really easy test to do. You take a couple drops of unknown, you put in sodium reagent, you heat it, and you'll get a yellow precipitate. If you get a yellow precipitate, you've got sodium. If you don't, you have 7 other possibilities, right? So the sodium test is very specific. It tests for one thing and one thing only. You could also think about the magnesium 2+ test, right? That test turns purple for everything besides magnesium. So if you go and you say, okay, I didn't have sodium. You did one test, you eliminated one option. Then you go and you say, okay, now I'll do the magnesium test. You put in the reagent, the magnesium reagent, and it doesn't turn blue. Now you've only eliminated one more of the 7, right? Each time you're only testing for one specific thing. Now we can go ahead and think about broad test. Now the broad tests are a little bit more difficult to think about because we have to think about where did I use this reagent multiple times, or how did this one reagent respond to multiple different things. So the example that I have on that slide is AgNO3. Silver nitrate precipitates with several things. It precipitates with chloride, bromide, iodide, carbonate? Oh, it's not on there. It precipitates with carbonate, but it's not on there. I forgot because I don't think that's an option. Sulfite those should be on there, but I can't remember the KSPs.
That's what I had questions about. Like, not some of them are question marks, some of them are big O's and little O's, and I'm like, I don't know.
Oh, the big O's and the big O's and O's. Let me take a look. Yeah. I can't remember what's on the slide. So, the big O versus little o doesn't really matter. I don't know if this is going to work. So it's this slide that you can look at on the general unknown lecture slides posted on Polylearn. The question marks are things that I couldn't find. I went to look them up and I was like, I'm not sure. I could not find that information. The big O's were something happened or don't exist, right? So if you look at the Ka for the conjugate of Cl minus, strong acid, you don't really find anything. Doesn't interact. So the things that are written down are the things that were important. So the KSPs, right? If you tried to look at AgF, doesn't precipitate. I couldn't find a KSP for it. If you look at AgSO3 or AgS2O3, I couldn't find values. I don't know if those precipitate or not.
Those are good question.
Yeah. So you could look at that and say, okay, the AgF, we did that test, and I know it doesn't precipitate. Right? We actually did that when we were doing our bromides test. Hey. Yeah, that's great.
Thanks.
When we look at AgSO3 and AgS2O3, the thiosulfate, we never even did those tests. So I have no idea what to expect. But there are a few things that precipitate. Cl, Br, and I. So if I form a precipitate with silver nitrate, I've cut like my 8 choices down to a group of 3 and a group of 5. right? That's different than just testing for one and eliminating one thing.
Yeah.
So then I can think about, okay, well, how would these things respond to the addition of acid, right? The ClDbr and the I would not dissolve. And just in case, let's just add these two others, even though I'm not sure. SO4 2 minus, SO3 2 minus, right? If silver precipitated with those. Oh, there's also Ag S2 minus, and that one should precipitate for sure. Silver sulfide should precipitate. Let's move sulfide up to this precipitates for sure list.
The X's mean that it does precipitate. So the
KSPs tell me if it precipitates or not.
right. X is an indication. Okay.
Yeah.
And what are in these columns? I'm just confused. Are these zeros or?
Those are, so I should have put infinity symbols there instead of zeros. Because when you try to, well, let's make, rather than just me telling you, let's look at that. So we're looking at the last column in this table. Why don't I have Kas for the conjugate of Cl minus? It's a strong acid. The Ka is going to be some giant number. Why don't I have a Ka for Br minus? The conjugate of Br minus. Same thing. And I minus. Those are strong acids. The Ka for F minus, we've got an acid that we could form. For S2, we've got an acid that can form. SO4, we have, do I actually have a Ka for that one?
You do.
Oh, that's SO3. SO4 also does. S2O3 does not. So we can now look at this and we can say, okay, out of these 1, 2, 3, 4, we've got 5, 6 things. We got 4 that will definitely precipitate, 2 that might precipitate, and 2 that won't. Notice this broad test does a really good job of splitting up the field of anions. I got 4 that'll precipitate, 4 that probably won't. It gives me a 50-50 split rather than just getting rid of 1. Now, after I have that precipitate, I can go through and start doing more specific tests for these things. One thing we can do is I can add an acid. If I add an acid, the S2 minus precipitate would dissolve, but the others won't because these are all strong acids. But the S2 minus would. So that would instantly say, okay, I'm going to go do the sulfide test and double check this result. We can do the same logic with SO3. Let's say, and now I don't know if SO3 is going to form a precipitate. Let's say silver sulfite does form a precipitate. It would dissolve in acid. Silver sulfate would dissolve a little bit in acid, but not much. So again, adding acid would give us this second check.
So is that the point of like adding H2SO4 in that like second
Yes.
part, that second section?
Yes.
Okay.
So that's where we can think about broad tests and specific tests. So what you have to start thinking about is, where did I use reagents in multiple tests? Where did I use the same reagent in like several different things, or one reagent that responded to multiple different things?
And in this example, that is silver.
Yeah, in this example, that's silver nitrate. We added silver nitrate, we saw how it responded. When you start looking at the sulfide group, KMNO4 is a great example, right? KMNO4 reacts with some of the chloride group, and it reacts with some of the sulfide group. So KMNO4 is another really good thing to look up. Okay, if I take my unknown and I add KMNO4, which things do I expect to happen? Because it's going to give me, like, it's going to cut out like 3 possibilities.
Okay.
But
So that's
which
one.
3?
That's included here.
Yeah, and I should have listed more, but I was in a rush.
So we should look up like if you added KMNO and then KMNO4,
What
would
happens?
precipitate.
Ooh, not precipitate, but what would react? It's a redox reaction with KMNO4. And you've already looked it up, actually, right, in your notebooks. Like, we've done all these tests before. Now it's just a matter of taking those 8 weeks of tests and like compiling them into like one informational set, which is why it was so important that we have good notes on all of our tests and results. Question?
This is kind of like a process question, just because
Sure.
like we have all this stuff and like I understand like what we're doing, but like I like guess like I'm kind of confused, like when I get there, like I have 3 hours to like do all this stuff. Like what is like kind of like an order of like steps.
Yeah.
Like you do a
And
flame test, and
when
then
do you have lab?
tonight at
Tonight?
6.
So let's think about order of operation. How do you
That's just, I
pick?
guess, kind of like what I was looking for like figuring out.
So how do you pick your order of operations? It really, the thing that's really interesting about this is there's no right answer. You can kind of go in any order. Now, there are some people who come in and they say, I'm just going to go down the list. I'm going to start with testing for chloride, then I'm going to test for bromide, then I'm going to test for iodide. You have enough time because we don't have the interference because you've only got one anion and one cation. You don't really have the interferences like we did before that slow things down a lot. So you actually have enough time to do all 16 tests. But that's also not the most efficient way to spend our time. So we want to start thinking about things that precipitate. That's an easy way to go. Trying to remember, what did we add that precipitated with sulfate and sulfite that then we dissolved? I can't remember. It was last week's lab. We had the sulfate test, and we added something that formed a precipitate. One of the precipitates dissolved with acid, one of them did not. And I'm totally blanking.
Strontium?
Yes, strontium.
Strontium. So one of the things you can do, now this is going to be a little bit tricky. So first thing that you're going to want to do well, let's change that a little bit. You want to transfer it to a beaker. Those little vials cannot hold 10 milliliters of water. And the directions say dilute your solid in about 10 milliliters and you'll get approximately the same concentrations you've been working with all quarter. So you want to transfer to a beaker so it can actually hold 10 milliliters and then add 10 milliliters. First thing, does it dissolve in water or not? Right? Now, we know that our salts have to dissolve in water. Just knowing the solubilities, the KSPs for all of the 64 choices, because we've got 8 anions, 8 cations, it eliminates, I think, 20 possibilities. So you're already down to 44 possible combinations rather than 64 possible combinations. After that, then you have to look at what's left and how you can differentiate them. Most people start with a flame test. I'm going to put a warning in there. Don't forget the flame test is not conclusive. The flame test alone, even if it does that bright green flash, that alone is not enough to say for sure you have barium. You still should go do the barium test. Now, interesting logic problem. Add strontium nitrate. Yeah.
And so flame test, that really can't tell us anything about the anion. It's only for the cation?
Correct. And a lot of times these tests will only give us information about them. You notice the silver nitrate only gave us information about the anion. The flame test only gives us information about the cation. Something you can do. Now this is, I should not put this one. Then we should pick our favorite prod reagent and test it out. See what happens. For some of you, that will be adding KMNO4 and seeing what redox reaction happens. For some of you, that'll be adding silver nitrate and seeing what precipitate forms and what color precipitate forms. For some of you, it'll be adding strontium nitrate and seeing if precipitate forms. Interesting thing, if you add strontium nitrate, because we knew it had to be soluble, if you form a precipitate, you know you don't have strontium, and you're going to figure out some information about your anions as well. It's a little bit of a logic puzzle, right? Let's think about this. I'm going to switch colors because this is a little interesting. So if you form a precipitate when you add strontium nitrate, you know you don't have strontium in your unknown because it just dissolved in water, right? If you had strontium in your unknown, you'd just be adding more strontium to your unknown, and it wouldn't precipitate. So by reverse logic, if a precipitate forms, you couldn't have had strontium because it wouldn't have dissolved if you did.
As in the strontium you added wouldn't dissolve?
Yeah. Yeah. No precipitate. If you don't get a precipitate with strontium, you eliminate, I think, 3 or 4 anions. You eliminate almost half of your anion choices. So that's kind of nice. And then you can go on and keep doing the test. So if you form a precipitate, you also might have a couple of the anions, and then you can start doing specific tests for them, right? So that's another good example of a general reagent, strontium. It reacts with sulfide, sulfate, sulfite, and I don't know about the chloride, bromide, iodide, right? Because here's the other interesting thing. We never added strontium to the chloride, bromide, or iodide, just like we never added silver to the sulfate, sulfite, thiosulfate, right? We never did that. However, in the classroom, you have all of those things. You can take a group of the sulfur nones, all the nones are still there, take a group of the sulfur nones, add silver to it, and see what precipitates you form. Write down the colors and see how it compares to yours. Sometimes just the color will be enough to be like, good clue, now I'm going to go do this specific test. Then we can get to like the specific tests. A lot of times for how fast, now, like I mentioned earlier, because we don't have the interference, since you've only got one anion, there is enough time to do all 16 tests and be very systematic about it. There's enough time for that. However, you might just get lucky. And at some point, there is just luck, right? You decide to start with the chloride test, and you don't have chloride, and then you just keep going like down the list. You decide to start with the chloride test as well, but you do have chloride. So you're instantly done, right? And it's just a matter of like some luck. But if you decide to start with the chloride test and you decide to start with the bromide test, then it turns out both of you are there for a really long time. So there's some, for how long it takes. I will admit, I have had, every once in a while, I have a student finish in 20 minutes. They come in, they get the green flame, they do the barium test, they're like, I have barium. They say, okay, first thing I'm going to do is the chloride test. It turns out they have chloride as well. And it's just because they started with the chloride test. I think I've also had that with, there's one of the fluoride is one that they decided to start with the fluoride test. It's a very specific test. They were doing a 1 in 8 chance, but they got it. And they're like, I actually have fluoride. And they were done with like all of the other possibilities right away. And then they decided, I can't remember, I think they had like magnesium fluoride or something like that. And it was just happened to be the first 2 tests they did. Finished. I've had students who are there for 3 hours because they do one test and they think they've got it figured out. And so they don't do another test that would have conflicted with their answer, right? They do the lithium test and they're like, I got an answer. And it's like, ooh, are you sure you have lithium? Because magnesium might interfere with the lithium test. We've never checked for that. So you gotta be careful about being overconfident in the things that you think you have.
What like specific tests, sorry, like fluorine or like that kind of stuff, would you like get kind of a more definitive answer? Like just so I could like test for those first, like if it's a definitive answer. So if I know like if I test for chloride, there's like absolutely definitely not because there's no like interference, like theoretically, like then I can immediately cross off and be sure.
Right. So that would be making your list of specific reagents. The fluoride test used that zirconium alzarin, the zirconium alzarin, or I can't remember. I think I'm confusing a reagent with an indicator. No, it's alzarin yellow. Yeah, zirconium alzarin. Yeah, it's very specific. Reacts with fluoride, turns from red to yellow. Sodium reagent, very specific, precipitates with sodium. Doesn't precipitate with anything else. Very specific, right? Now, the sodium test still, I would say, doesn't give you a very clear answer because the amount of precipitate you form in the sodium test is so minimal that even a little contamination might give you a false positive, right? The sodium was always really challenging because there were a lot of false positives with that. The magnesium test, really obvious. Remember how blue it turned? Like that was, I know that was a couple weeks ago, but it was that one where it was like, I had people coming up with purple solution being like, is this blue? And I was like, go check with magnesium. And they went, oh, that's blue. So like making sure that we remember and have like, hopefully we all have really good notes about what our results were from the last 8 weeks. So that way we can just be like, chunky blue. Okay, now I know what that is because I got the same thing. I'm trying to think of some other really specific tests. I remember the chloride one's a little bit tricky, right? Because you had to like precipitate and then redissolve and then precipitate and then redissolve. The iodide test was pretty obvious, right? You got that purple xylene layer. You had to do a lot to get to that point, but it was pretty clear when you had it. There was not a lot of second guessing when you got the iodide. But yeah, you just got to go back through your notes and think about those specific results. Question?
So I'm guessing this is kind of an obvious answer, but you're only allowed our notebook? Is that the...
Yeah, in my class, you just are allowed whatever in your notebook, permanently attached.
Right. Nothing else?
Nothing else. But I've also had students who just have all of the labs stapled in, and I'm like, it's permanent.
That's okay.
Yeah.
Okay. Cool.
Yeah.
Definitely.
So do we need to worry about random things like carbon dioxide dissolving in the water that could possibly cause interference with? Yeah.
Yeah.
Okay.
Yeah,
Okay.
that happens.
Yeah.
Right, and there's specific measures for dealing with that in the lab procedures. Carbon dioxide has not gone away. Other questions? I know this is a lot to think about. Mostly don't stress about it too much. You've got the lab experience. You just have to apply it. It just feels really scary because you've been told what to do for the last 8 weeks, and now you get to decide what you do. But it actually usually goes okay.
You recommend doing tests in different tubes, or just kind of keep it all in one tube, or is there?
Definitely different tubes, because you can always run into that issue of, like if you're doing a fluoride test and then you're doing a sulfide test, there might be some interference that we never looked for before.
Yeah.
And that can create a big headache. So definitely, and it's also one of those situations, if you run out of unknown, you can go to the stockroom and get more. But you're using 2 drops at a time from 10 milliliters, so you should have plenty. Other thing I'll suggest, this is a good idea. Take a picture of your solid before you dissolve it, right? The solids, and you can, there's no rule. Well, I guess if you're only using your notebook, you can't do this. But one of the things you can do is you can look up what crystalline solids look like. And you can actually have an idea of like, oh, this totally looks like this solid. I'm almost to the point where when I look at an unknown, I have a guess of what it is, just from like the different crystal structures. I've done 129 lab enough times that I remember like, oh, big old chunky things are probably this. I'm not going to say what. That's for you to figure out. Other questions, or should we move on to midterm and homework 6 stuff? Is it okay if we do homework 6 things before the midterm? Okay. What homework 6 questions do we have?
I was confused on like parts, like just making sure or like understanding how you go about the different parts of like 8 and 9, and then from then like 10 and
Okay.
12, and just like stuff about the geometry and the electron configurations and all that stuff, because I know we went over in Chem 127, but like we flew through it, and I honestly don't think that I really understood it.
In 127 or 129?
127.
Okay.
And
So,
129.
Let's start with well, yeah, you know, I was operating under the assumption that you had your 127 knowledge, so I could go a bit faster.
Yeah. I mean, like every professor is different for 127, so
Yeah.
Yeah, probably. Yeah.
Careful, this is being recorded. Before you say too much. The troubles of doing office hours live. It is a pretty good microphone, so definitely like.
They don't know who I am, so.
Oh, fair. That's true. That's part of like why I don't have any of you on campus. You could probably, you know, talk bad, but I prefer you didn't. So problem eight is honestly a bit of review.
Yeah, it's
Problem eight,
like
A, B, and C are all review from homework 1.
Could you just go over B, because I know, so like the pH is 3.
Yes.
And
Okay.
so I know that means it's like more acidic and you have more H+, but HI forms a strong acid, but I wasn't sure if that was like.
No, you're totally right. So if it forms a
Okay.
strong acid, so we're looking at the solubility of AgI, which has a KSP associated with it of. Did anyone look up the KSP for AgI?
Oh, it's 1.5 times 10 to the minus 16.
Pretty insoluble. In pure water, we're just doing our ice tables. In water with a pH of 3, so decreased pH. Here's the question. Will a decrease in pH affect the solubility of AgI? Thumbs up for yes, thumbs down for no. No. Why not? When we look at the possibility, right, we know that AgI will break apart into Ag plus I minus. Then we say, okay, if I add H3O plus, it's not going to react with the Ag plus, it's going to react with the I minus. That will form hydroiodic acid with some H2O that I don't really care about. This equilibrium, since this is a strong acid, this equilibrium is totally one direction. And it's I minus. Turns out your answer to part A and your answer to part B are the same number. Since pH does not affect the solubility of silver iodide, since pH doesn't affect the solubility of silver iodide, it's the same answer.
So if it was a more basic solution, then you would react it with OH and then it would be affected, right?
You would run into the problem of potentially forming silver hydroxide, and that would be a competing KSP value. So we'd have to look at the KSP of silver hydroxide and then do a precipitation competition.
Okay, so you just don't worry about the OH for this
No.
at all. Okay.
Right, because this particularly said a pH of 3, so it was more acidic.
Okay.
Part D is where it gets interesting. Should we do part D?
Mm-hmm.
So part D is, what's the solubility of silver iodide in a solution that is 0.91 molar sodium cyanide? Where now we're going to have this competition of the silver and the cyanide. I'm going to pick which way I write this, and we get to pick. I'm going to write it for the complex being formed. In this, we are told the complex formation of AgCN2 minus. What is the name of that complex?
Is this like
I'm actually asking, how would you name this complex?
Is it bi or di? Dicyanate arginate?
Dicyano, right? We switched the 8 ending on the anion ligands switch from 8 to O. So it's dicyanoarginate. Of course. Practice those. That's something to be comfortable with. So we know that the KF is a big number, and it's bigger than the KSP is small. So I'm going to choose to write this reaction in terms of the formation reaction. So I'm going to have AgI plus, when I look at the reactants, I have the solid in the Cn minus solution. So this is my reactant. So I also want to write it that way for this reason. Is going to go, I'm going to already predict that it's going to be product favored, is going to go to AgCN2 minus plus I minus. When I calculate the K reaction associated with this, I'm going to write the K reaction a little bit lower. I want to give space for what I think will be a stoichiometry table. My K reaction is going to be, notice the formation reaction is going in its forward direction. So it's going to be my KF. My precipitation reaction is also going in its forward direction, right? I've got a solid going to ions. So that's already forward. So I'm just going to do KF times KSP in that case. I can get the numerical value. Calculator's out if you don't got your calculator out. 1.5 times 10 to the minus 16 times 1 times 10 to the positive 21. I might be able to do this in my head, but please do it on the calculator to make sure I'm not wrong.
That's what I thought of.
Yeah.
Did you get your?
Watch out for an email from me. I have to go sign a lease, but I'll
Okay.
be in office after.
Great.
Sorry.
1.5 times 10 to the positive 5. Very product favored. So that means when I look at this, this is going to be essentially stoichiometry. Oh, I did have something specific. So in order to do the stoichiometry, I need the specific volume. I've got as much silver cyanide. I've got, now I can start doing my stoichiometry. 0.91 times, let's just go full moles, right? Times 0.6 liters. It's going to give me my moles of cyanide. I'm doing a reaction because my K reaction is large. Yeah.
So how did you know from the beginning that you'd be doing a stoichiometry table?
So I was estimating because I looked at the size of my KF and the size of my KSP, and I said my KF is more big than my KSP is small, right? 10 to the positive 21 versus 10 to the minus 16. When I make that comparison, I say I'm going to end up with something that's going to be positive exponent still, which means I'm going to have a large number. So I knew that I was going to be very product favored if I wrote it down this way. Now notice you could have written it down the reverse way, but you don't have any I minus as a reactant. So as soon as you went to do your stoichiometry or your ice table, you'd have a 0 in your reactants. And having a 0 in your reactants would essentially say the reaction can't happen. So we actually can only write this one direction because we've got the solid and we've got the cyanide. 9.91 times 0.6. I can't do that.
0.546.
Oh, that totally makes sense. I should have been able to do that because 0.91 is almost 1. So it should be just a little bit less than 0.6. In terms of AGI, right, we're trying to figure out how much AGI we have. So for now, I'm going to say excess, but this is kind of like the thing I'm trying to solve for, right? I'm trying to figure out how much AGI I can break apart. So right now, we're going to be reaction dominated. I'm going to have minus 0.546, minus 0.546, plus 0.546, plus 0.546. And then I've got to go back. Notice we've gotten lazy with our mole ratios because everything's been 1-to-1 for the last 3 weeks. This is not a 1-to-1 mole ratio. I'm going to have a 1-to-2, 2-to-2, 1-to-2, 1-to-2. Don't forget the mole ratios. So this thing is, of course, going to go to 0 because it's our limiting reactant. Technically, we want this thing to kind of also go to 0, right? Because we want to find the correct amount to react. But we have as much as we need. We're finding how much solid we react because this is solid. This is aqueous. This is aqueous. This is aqueous. We react in this case. What's 0.546 divided by 2?
0.273.
So at this point, with adding this much, I have 0.273 moles reacted. And there's probably still some solid left over, right? But that's how much I've reacted. I end up forming 0.273 moles of the complex and 0.273 moles of the I minus. Am I done? Can I have a 0?
No.
No. So if we just said 0.273 moles reacted, which means it looks like 0.273 moles of the solid dissolve, which gives us our solubility, that would give us an overestimation because we know that cyanide is not going to go to 0. However, when we look at this, do you think the reprecipitating or the reformation of the solid is going to be significant in this case? Why not? Which direction do we want to look at the reaction now? Yeah, we want to look at the K reverse. It's going to be 1.5 times 10 to the positive 5, 1 divided by that, inverse of that number. I can't do inverses in my head.
Wait, you said it'd be
9.8 times 10 to the minus 6.
6.67 times 10 to the minus 6.
yeah.
6.67. 1.5 is nothing like 1. I don't know what I was thinking.
So it's 1 divided by 1.5 times 10.
Yeah, right. So if we're flipping the reaction and we're going to AgCN, I'm not giving myself enough space to do this, but hopefully we're right and it doesn't really matter. Plus I minus goes to AgI plus 2Cn minus. I've got a small value now. I'm going to have to switch to doing an ice table. Right, so this is just like when we were doing our precipitates, stoichiometry, ice. It's just now we need to calculate what our K reaction is. And I definitely need more space to finish this. But let's think about this. Yeah, question.
Is there not any I minus that, you're not considering like any starting, or I guess it
I minus is here.
No, I know, but like on the first reaction, like technically you're starting with, okay, I think I was just confused because I've seen a problem worked like this, like by my workshop leader, but he just went straight to an ice table, which makes more sense why there's I minus to start with, so never mind.
Yeah. Probably
okay.
jumped over the stoichiometry because the stoichiometry just goes to completion, right?
Mhm.
And if you remember, when we were doing competitive, this is like competitive solubility. And when we were doing competitive solubility, we skipped the stoichiometry table because it always went to completion, right? Notice I can just jump to what's my I minus concentration. I 2.73 divided by 0.6, right? Because I need to switch my moles to molarity. So I'm going to take my moles that I made divided by my total volume. We're going to assume that adding the solid didn't really change the volume. This will get us our initial. I can't divide by 0.6 in my head.
0.455.
0.455 molarity, 0.455 molarity. Don't care because it's solid, and 0. Now we know we have to go back a little bit, but notice if we're going to use the x as small approximation, my change in I minus is going to be negligible. My change in the metal complex formed is going to be negligible, which means also the change in the solid will be negligible. So we can kind of ignore the ice table and just say, my solubility is completely determined by the reaction step. Now, there's another question we could have asked that would have been a little bit more complicated. And I think there's a later homework question on this. I know there was definitely a lecture slide example like this. I could have also asked, how much cyanide is left in solution at equilibrium? In that case, you have to do the ice table. If I just ask, what's the apparent solubility? Then you can just do the stoichiometry as long as the x to small approximation is good. In this case, the x to small approximation is probably going to be good because our k reverse is pretty small.
Answer would be 0.273.
Your answer would be 0.455, right? For the molar solubility.
Of the silver iodide.
Yeah. The molar solubility of silver iodide in 600 milliliters of 0.91 molar solution of sodium cyanide would be 0.455 molar. Should be a pretty dramatic increase from part A and B. Like 10 to the 21 times more soluble. Right? Having that metal complex formation dramatically changes the apparent solubility.
So wait, how did you get the 0.455 again? Like,
It was the moles we have divided by the total volume, right? Molarity.
okay.
And the reason that I can say that this value is the molar solubility of AgI is because I've got this 1-to-1 ratio, right? All of the silver in solution in the complex came from the silver solid, 1-to-1 ratio.
Okay.
Question?
So can you explain again how you knew that AGI would be in excess?
Imagine that you were doing this in an experimental setting. You got your tub, you got your big beaker of the sodium cyanide solution, and what you're doing is you're just tapping solid in until you see it not dissolve, right? And you've got a whole pile of solid, and you're just going to keep adding it a little bit at a time until you see it not dissolve. So we essentially get to pick this value.
Okay.
I don't have my lab.
It's outside the door.
Okay.
That's why everyone's freaking out. Just sorry, that's interruptions.
Okay. So that's how we do problem 8. Problem 9 is almost exactly the same. Problem 9 is asking you, instead of doing the solubility, precipitation, competition, is just asking how much complex ion is formed. And in order to do that, you're going to do the reaction, and then you're going to do the equilibrium. And you're again going to find that the reaction is going to dominate because the reverse reaction, you're going to be able to use X as small. Oh, actually, no, you're going to have to do the ice table because this is an example which asks you to figure out the concentration of silver in solution.
Do you have the answer for it on there?
No.
No? Okay.
Should we work it out? Did you work it out?
Yeah, I was just, I thought I was confused on that, but I actually think I did.
Did you get a very small number for silver left in solution? Does that make sense?
Yeah.
Yeah. We expect a small number because
want to go back.
the formation, so let's write down the formation of this react. Let's write down this formation reaction. This is going on to problem 9. And let's just do some logic for this instead of getting directly into it. Homework 6, number 9, we're looking at the formation. So we're looking at AgNO3 plus, what do we add in there?
AgNO3 and NaCN to form AgCN.
So we're doing this thing again. Very similar to the last thing that we just did. Actually, almost a little bit easier. Awkwardly, I've got a different KF in that problem. I must have just looked it up someplace else. That one has 3.0 times 10 to the positive 20. Same ballpark. Right. So what this tells us is, and again, we can get rid of our spectator ions. We can get rid of the nitrate. We can get rid of the sodium. Those are spectators. We've got Ag plus. We've got, that's an awkward looking C now. We've got Cn minus. We know that this reaction, because of this large KF, is essentially going to be completely towards products. So we should expect a very, very small amount of silver left in solution. Something on the order, something on the order of 10 to the minus 18.
I got minus 22.
Also possible. Yeah. Really small value though. So that's number 9. There was something else on the homework, and then I want to make sure we have midterm question time as well.
Oh, I was just gonna.
Oh, right.
Yeah, I left.
Thanks. I'll take a look at that in a little bit.
Oh, could we look at 10 and or 12?
Sure. So let's keep going with the homework. We didn't solve number 9. We just looked at it logically. But it's just going to be stoichiometry ice table like we did back on homework 2. So, so that's part of why I went through, like, if you're like, whoa, we didn't do this in class enough. See ya. It's a bunch of old concepts used in a new way, right? It's the same stuff we've been doing since week 1. Yeah. It's really all been stoichiometry and equilibrium over and over and over again the whole time, which is part of why I really don't want them to change the class, but they're talking about changing the class.
To what?
They're talking about moving, well, we'll get into that later. Let's focus on homework 6 number, what was it, 10?
Yeah.
Homework 6, number 10. Let's see, what is number 10?
Do you want to see it or do you want me to read it?
Yeah, here, let me just take a look at the paper. 10, transition metals on the common line sheet. Can you justify common oxidation states based on electron configurations?
Sorry.
It's a 127 question. No, that wasn't at you. That was me grinning at the problem. That's a 127 question.
Is oxidation state the same as oxidation numbers?
Which is the same as charge.
Okay.
Can you wait, are you gonna like go through that problem?
Yeah, let's look at silver real quick. So we have to remember how to do electron configurations from 127. So if we look at silver, now I need a periodic table. Please tell me.
I have a periodic table.
Please. I feel like I should just have periodic tables everywhere. They're all in a pile right over there. So if we look at silver, this is element 47. We're going to have krypton. And we're going to have our 5s2, 4d9. And that is wrong. Don't write that down. Right? Because whenever we see that d9 you're going to get your full shell bonus. Do you remember the full shell bonus?
Is it where like you fill up your d orbital first and then you go to your s?
Not exactly. So,
Like you share it, like they're on the same level.
yeah, they essentially become, so essentially what happens is, as we put electrons in, the d orbital and the s orbital get very close to each other in energy, and actually the d orbital becomes a little bit lower, and it becomes energetically beneficial to have a full d orbital. So we call that full shell stability. It happens with copper, silver, and gold. Now, so this is silver's correct electron configuration, and we look at this and we say, how many electrons could silver easily lose? One. It could easily lose this one electron, right?
Oh, I mean, it makes sense that it has a +1 charge.
Yeah.
Wow.
It could easily lose that one electron and become a G+, which would be krypton or D10. And it turns out that's the most common oxidation state of silver, so common that we don't even write the Roman numeral for it most of the time. Like, we usually do not write silver 1, even though that's the correct international standard. It's a transition metal. You put the oxidation state in a Roman numeral in parentheses as a Roman numeral. For silver, we often get lazy because it's pretty much always silver 1. And then we got to go through a couple other examples. Let's try iron. Iron's a little bit trickier because iron has multiple possible oxidation states. Silver pretty much just has one. Iron has 2 really common and a couple other oddities. First thing we have to do is get the electron configuration for iron correct. Going to be argon, 4s2, 3d, I've got to count, 3d6. And we say, okay, this is the electron configuration. What things would be energetically beneficial? Again, we want to think the things that are beneficial. Full shells, half shells are beneficial. So if we look at this, we could imagine, what if we lost both of the s electrons, right? We've got 2 s electrons there to lose. They're the furthest out. We could go to iron 2+ and have argon. I'll put the 4s's there as 4s0, even though normally we wouldn't. 3d6. So iron 2+ makes sense. Lose both s electrons. Empty that shell. What else could we do?
Wait, I have a question about that.
Sure.
So I don't understand how that's more stable to lose the 2 s electrons when you still have 3d6 and then it's like not like.
So we have to remember something about electron probability distributions to really understand that, which you learned in 127 as well.
Yeah.
These pictures, right?
Yeah, I remember those.
Versus that. So the main thing you should remember is that the D, the 3, the N value out front tells us how close we are to the nucleus. And it turns out that the 3Ds are closer to the nucleus, so they're harder to lose after they're full. Right? After we put electrons in the D orbital, they are harder to lose because the S electrons are actually further away from the nucleus than the D electrons. So we almost always, the guiding idea, the kind of rote memorization thing we learn from that is in transition metals, we fill the s orbitals first and we lose the s orbitals first.
But why, like, I just don't understand, I guess, why you would have Fe2+ even be a thing because then 3d6, there's still like, it's not like half shell, like single half shells or full shell.
Right. So this is actually not the most common
That's
kind
not
of
the most
iron.
common. Okay.
It is a kind of iron you do find in the natural world, but there's one that's more common, that's more likely.
3.
Fe3 plus. Why Fe3 plus?
Because then you have a half LD orbital.
Yeah. Let's just jump straight to it. 3d5. That's actually the most common kind of iron ions. This is rust. Iron oxide. You don't form iron 2 plus oxide, you form iron 3 plus oxide because the half shell stability makes it more likely.
So the half shell stability, like, what does that make it more likely to bond with other things?
Well, it more makes it, no, it's not about it bonding with other things. It's about it losing electrons and how easy it is to lose the electrons. And when you have something like oxygen, so if we're talking about rust, you've got iron metal, right? You can also just have iron metal. Iron metal's everywhere. We make things out of it. It's all over the place. So you've got iron metal, and it's only when we start interacting it with other things like oxygen. Oxygen comes by, and oxygen's more electronegative, so it starts stealing electrons from the iron. And the question becomes, well, how well can it steal electrons? It turns out it can steal both of the s electrons pretty well, and it can even steal one of the d electrons pretty easily. After oxygen steals all 3 of those electrons, it can't steal anymore because the energetics of oxygen taking that many electrons and trying to steal to go below the half shell stability, it's just energetically not beneficial. So I'm trying to avoid the idea of like there's this problem with people saying oxygen doesn't want any more electrons. Oxygen doesn't have any wants. It's not conscious, right? There's just no energetic benefit for that.
Okay.
So when oxygen comes along and starts trying to energetically steal another electron, after it's already taken 3, the energetic benefit just isn't there anymore.
So,
right, and that's in typical environments. Now we can go to all these weird environments where we make very special oxidation states. Let me check something on my phone real quick. I know that's a weird thing to say during office hours, but I have this really cool app on my phone for the periodic table. And it lists the common and the uncommon oxidation states of elements. And I just want to look at iron real quick. So iron, where is it? Oxidation states. Iron's common to oxidation states are 3 and 2 and 0, of course, right? Iron metal. It can also go to an iron 6 plus, which I've never actually heard of. I don't know what that would look like. That would be losing 3 more electrons. That's really unusual. I don't know how to explain that energetically. It wouldn't happen. It's one of those things that you'd create like under high pressure, like deep in the earth, or high temperatures close to the core. The really weird one that I cannot explain that's on this list, iron 2 minus. That seems really weird to me, right? And there's going to be some really, like, that's not something that's going to happen out in like the normal environment where we see iron on a regular basis. Iron 3 plus is, but we can create really weird situations. Technically, in laboratory settings, we could probably even make iron 1 plus and iron 8 plus in experimental settings by controlling the material properly.
okay.
Not easily, but we probably could. And we just want to look at what's naturally most likely, and that's why we're making these energetic arguments.
So is it naturally more likely to be Fe3 plus because anything that's more electronegative, like the energy benefit only works until it reaches half shell or full shell stability?
Typically, yes, right? And that's where we have to be careful because there's definitely things that could steal electrons better than oxygen. And if we put those other materials in the presence of iron, that's where we get these weird possibilities.
Okay.
Right? But since we're talking about the oxygen environment that we're in, it's really the energetic benefit of the oxygen interaction.
Okay.
And then after you have iron oxide, then you can have all kinds of substitutions and things to make like iron chloride and iron bromide and iron iodide, and you can start changing the things around, changing the ionic bonds.
How do you determine ligand geometry when the coordination number is 4?
Periodic table, right? So, which question is that?
Well, it's question 12, sort of, not like.
Okay, are we good on question 10? We spent a lot more time on it than I thought we would, but 127 review. It's important sometimes. So, let's go ahead. And was there something with question 11 before we go to jump to 12?
It's what are the geometries for complexes with coordination numbers 2, 4, and 6?
Oh, that's question 11?
Yeah.
That's just definitions for us at this
Yeah.
point. Question 12?
It's like applying that, basically.
Fantastic. So remember, we essentially have that slide we looked at where we said there are some special exceptions that form particular geometries. I shouldn't have given that back to you yet. Because I need the periodic table to figure it out. Zinc, cadmium, and mercury 2+. Let's not do mercury. Zinc and cadmium 2+. Got a tetrahedral. Manganese. Manganese 2+ can also exhibit tetrahedral behavior, but we don't see a lot of manganese complexes. It's zinc and cadmium 2+ are the common ones we see that form the tetrahedral geometry. Why?
Why are you looking at me?
Oh, I don't know, because you're the only one looking at me. Everyone else is writing things down.
Isn't it because of the valence electrons?
Yeah. So if we looked at zinc 2+, let's go ahead and do the same thing we just did. We're going to look at zinc. I always like to start with doing the element before the ion. Zinc is going to be argon 4s2 3d10. When I go to the common charge of argon, now you all know what the common charge of argon is going to be. Lose both the s electrons, leave the d orbital full. It's going to make our zinc 2+. It's going to be argon 3d10. I'm going to write something weird over here. 4s0, 4p0. Right? We forget sometimes that these orbitals exist even if they don't have electrons in them. Right? That s orbital and that p orbital is still there, and we can still have other materials interact with them. Zinc doesn't have any more electrons to interact with those orbitals, but if we brought something that was going to donate electrons to zinc, it could do so into these orbitals. So we end up forming sp3 hybrids using those empty s and p orbitals, and that gives rise to the tetrahedral geometry. And if you're making that furrowed brow when you're watching this video and you're like, I don't remember this, I don't like that explanation either. Hybrid orbitals are a shortcut. So if we think about how we talk about orbital theory, we've got atomic orbitals. That's our s, our p, our d, and our f. And then we've got our molecules. And we've got our molecular orbitals. That's going to be sigmas and pi's. I don't know if we actually go to deltas. I've only seen it in terms of sigmas and pi's. And then you get into point group symmetries. Someplace in the middle here, where I'm not talking about molecules, molecular orbital theory would be the right way to do it. Atomic orbitals works great for individual atoms, but when I start making molecules, like metal complexes or anything with covalent bonds, I should be doing molecular orbital theory. The problem is you need to do quantum mechanical calculations from first principles in order to get your molecular orbitals right. And everyone makes that face and that noise when I mention that. Organic chemists as well are like, no, that's just too much work. Come on. It turns out someplace in the middle, you got hybrids. Hybrids are essentially combinations of the atomic orbitals that get us some of the properties of the molecular orbitals without having to do the full quantum calculation. And the ones that remember is we've got the SP, the SP2, the SP3. Those were from 127. That's our linear, our trigonal planar, and our tetrahedral. And those are the ones that the O chemists care about because those are what happen on carbon very often and give us the different molecular geometries for organic molecules. And while we're doing our ligand field theory, our metal complexes, we've got a couple others that we care about because transition metals bring along those d orbitals, and we can end up with an SPD2. Let me think about this. I think that's right. Oh, no, I'm wrong. It's SP2D. That's what gives us the square planar. And then SP3D2. That gives us octahedral. And the hybrid orbital theory does a great job getting the geometry. But what we're going to find out pretty soon as we move on to ligand field theory today is it gets us the geometry, but it doesn't get us the energy levels correctly. So we're going to fix it by doing ligand field theory to get the energy levels. And then we're going to realize that it doesn't fix it entirely in a predictable way. So then we're going to say, okay, let's just do molecular orbital theory and get it right. And that's why we're going to move on to molecular orbital theory, because molecular orbital theory is the right way to do it. But it's always this cost-benefit analysis of hybrid orbitals get us 70% of the answer with 10% of the work. So if you only need that 70% and you don't need that like details of the energies, why would you do all the extra work if you don't need that information?
I'm confused. Like, we learned about hybrids in a very, very weird way when we did it, and like very weird models.
How?
Like, we had these crazy things that we had to draw that no other class had to do. That like we asked our
Atomic orbital overlaps?
Like,
I was like this, right? When we had these.
we had to like draw all the like different things, and like I don't know, it made like no one knew what was going on at all.
I think you're talking about the atomic orbital overlaps.
Yeah,
I make
like,
my class do that as well.
Yeah, it was a
Yeah,
mess,
so you're
but-
talking about like your s orbital
Yes.
plus your p orbitals give you.
Yeah.
Yeah, I make my class do that.
Yeah.
You're not the only class.
Okay,
it was not
good,
the only
'cause,
class.
like none of my friends had to do those things. But anyways, like I'm just confused, like what the
What this
hybrid stuff
means?
even means. Yeah, because we never really talked about what it meant. So I'm very.
How much calculus have you done?
I'm in Calc 2 right now.
Have you done differential equations?
Yeah.
Great, we can explain it with differential equations if you got a minute.
Yeah.
Let's do this real quick. This is you know, and this is one of those things where it's kind of like, do you need to know or can you just remember? You can just remember. But let's talk about this real quick. Here's a differential equation. What's a good f of x we could use for this? We want the second derivative to return the same thing. Yeah. Now, we're going to want e to the kx because we want a k to come out of it. And we also want it to turn negative. So what times itself gives us a negative 1? Imaginary, right? So e to the ikx would be a solution to this. What's another thing that taking the derivative of twice returns the same thing back? Maybe with a negative sign out front.
Negative cosine or negative sine.
Yeah, actually you could even just do sine of kx, or you could do cosine of kx. those all, if I do sine of kx, it gives me cosine kx. I take cosine of kx, it gives me negative sine kx. You know, I get the same thing back, and this statement would be true. All of these are valid solutions. Actually, I can think of another one. E to the negative I kx would also return the same thing. All four of these are reasonable solutions to this differential equation. You might not realize it, but you just solved the Schrodinger equation. That big, scary equation that maybe you looked at, maybe you didn't look at, that you derived from quantum mechanics. This K is going to include the Coulomb force interactions, the motion of the electrons, some energetic interaction, and you get these kind of limitations. So you end up getting a limitation that you're going to have something that operates like a sine function, that's going to have constructive and destructive interference, that's going to have, you know, hills and nodes and valleys, the same types of things we see with our electron probability distributions. Now, here's where the hybrid orbitals come in. So essentially, if we solve this out for the Schrodinger equation, we wouldn't get something as simple as sine kx. We'd get something that's a little more complicated. It's really going to be like exponential-like functions, but we'd get some answer. And we're just going to label that answer as the s orbital. We get a second answer because there's a second function that works. We're going to label that second answer the p orbital. We get a third, and the p orbital has like 3 different answers, you know, where we just change the sign of something. So we're going to label them like p1, p-1, and p0, depending on what like number we're multiplying by up there. And that's really where all of these different orbital labels come from. Here's the catch. If sine is an answer and cosine is an answer, can I add those two together and also have them be an answer? Could I have sine kx plus cosine kx be an answer? What we call a linear combination. Taking the derivative distributes, multiplying by k distributes. So yeah, that would work. That would work. It would be like the same thing. This combination of answers is saying, look, I'm going to take an s orbital, I'm going to add it to a p orbital. I'm going to take what's called a linear combination of atomic orbitals. I'm taking 2 answers that work by themselves, and I'm putting them together to make a new answer. That new answer reveals different properties of how the orbitals interact together. Because keep in mind, when we're looking at an atom, just a carbon atom, it has the s orbitals, it has the p orbitals, it has all of the orbitals. Drawing the pictures individually doesn't tell us the whole story, because the atom by itself has all of the orbitals. All of the orbitals can interact in many different ways. So we're going to take a linear combination to see how those orbitals interact when we start to bring in something else, right? Because we only talk about hybrid orbitals when we have an atom interacting with other atoms. And that interaction changes how the orbitals look. I don't know if that simplified things or confused things.
I'm still just confused, like how, like 4s0, 4p0, you know that it's an sp3 hybrid, like all of that, like how?
Oh, so in that case, I hybridized all of the possible orbitals, right? I wanted to, because I've got an s and I've got 3 p orbitals, right? So this 4s0 would be like 1 line, the 4p would be 3 lines. All of them are empty. All of them have space to hybridize. All of them can take in donated electrons from a ligand. If we did the same thing, instead of doing zinc and cadmium, if we did copper or silver +1, we would find that we have sp hybrids as well. If we did nickel or palladium or platinum +2, we would find that we have space in the s orbitals, the p orbitals, and the d orbitals. And we end up forming the sp-d hybridization. Now, if that still seems like wishy-washy magic to you, hybrid orbitals are kind of wishy-washy magic. We should really be doing molecular orbital theory. It's just, again, molecular orbital theory you can't really do on paper. You have to do with computer simulations. And it's, again, like Do I want to do 80% more work for 10% more answer? Usually no, but sometimes yes.
So could you do an example of a square planar and like how you know that it's sp2d then?
Yeah, let's go ahead. I'm going to erase all of this differential equation stuff. Sorry to anybody who didn't take differential equations. That was really confusing to you. You should take differential equations. You learn a lot. It's probably one of the most important things for understanding how things interact with each other when they're changing. And since change is always happening, it's super important. Sorry for math there. So let's go ahead and look at nickel plus 2, palladium plus 2, and platinum plus 2. These typically go to square planar. Right, and now this is typical. Some of these will go octahedral, right? They'll have 6 things attached to them. But let's look at how they go square planar first. So let's do nickel. Nickel's electron configuration is going to be argon, 4s2, 3d, 3d8. When I do my nickel plus 2, I'm going to do argon, 3d8, 4s0, 4p0. And what I want you to realize here is when I write 3d8, let's go ahead and write, instead of doing the electron configuration, let's do the orbital diagram. Two, 3, 4, 5, 6, 7, 8. I've got space left over in my d orbital. When other things start to come along to interact with this, these 2 electrons can actually get forced together, leaving me with a D, a S, and some P's. So that's going to form an sp2d hybridization. Now, if you're like, wait, why didn't you get that last P? That's where you start to go octahedral, right? While nickel plus 2 is one of the only things that can go square planar, it could also sometimes go octahedral if you had the right things donating electrons to it. And remember, this list of what goes linear, what goes tetrahedral, what goes square planar, those are the weird ones, right? And that's why we're learning we're kind of learning this through exceptions, right? Those are the things that are exceptions. Pretty much everything can also do octahedral. I think silver plus 1 and gold plus 1 and copper plus 1 are some of the only things that don't go octahedral ever. They only go linear. But even copper plus 2 can go octahedral.
So sp2d is square planar. Like, how do you know again that that sp3d is octahedral, and why is there the cutoff, or is it just something that we need to memorize that sp2d is square planar?
Well,
I'm just confused why you don't include the third p.
So including the third P is something that can happen. This is where we're going to have to start talking about ligand theory today, or tomorrow. It's not Monday, tomorrow. Because when we start talking about why don't you include that third D, why don't you, it starts to depend on what's donating electrons as well, right? Right now we've got space for 2, 4, 6, 8 electrons, or 10 electrons if we included that last one. So it becomes a question of what is donating electrons? How well does it donate electrons? How well does the ligand that we're attaching interact with the orbitals on the metal? And we're going to find that hybrid theory doesn't really answer it for us. Right? Hybrid theory is kind of a thing you memorize so you don't have to do a bunch of extra work. And that's honestly what I use to say, okay, I don't like memorizing things. Mm-hmm. I don't like not knowing why it happens this way. Let's do molecular orbital theory and actually look at it.
Okay.
And molecular orbital theory, unfortunately, I will tell you this. Unfortunately, we are not going to get to do molecular orbital theory justice. We'll do it in 2 days when there is actually a class that takes 10 weeks to get to molecular orbital theory. It goes through the differential equations we did. It actually goes through solving the Schrodinger equation and then interacting different atoms in order to get the picture. It's actually the third quarter of like a P-Chem. So it's actually like a year-long course to get to molecular orbital theory. And we're going to do it in 2 days. So if you're like, this is really unsatisfying and I want to know how it works, you should become a chem major and take P-Chem.
I think I'm gonna pass. Thank you.
That's also fair. I think it's really interesting. It's actually part of what I do my research on.
Orbital
I
theory?
I'm trying to do, I have not worked on it for a while, but I'm trying to do condensed state orbital theory. So like solids and materials, and most people don't do it because it becomes a big mess really fast because you've got so many atoms interacting with each other at once that a lot of the approximations that make it easy start to break down. And I'm like, all the easy stuff's been done. Let's do something hard.
Yeah, did you tell us in class that you like spent an hour and a half trying to
yeah.
disprove the shortcut? So I feel like this is good research. For
Yeah. I accidentally used an hour and a half to prove a shortcut work. I should have just trusted the shortcut.
Never trust the shortcut.
Yeah.
That's rule number 360 of life.
Good to know. So that is problem 12. It is a little bit of memorization at this point because we are using this linear. So like the fact that it's an SPD2 is an energetic argument from linear combination of atomic orbitals, and we're just not going into that, right? We don't want to go into, I mean, some of us might want to go into that, but none of you want to go into that. So
do we just have to remember like basically those exceptions?
Yeah.
Okay.
And I don't remember them. I have to look at the periodic table every time.
Okay.
Because it's just on the periodic table. Right? That's why I have that boxed picture on the slides, is because you can just look at the periodic table and there it is.
Okay.
Mercury does other weird stuff. Yeah, sorry,
Am I
Claudia.
able to get my chem intern?
Yeah.
Oh my.
Yeah, got both of those. What other questions do we have?
I can just come back and ask about the midterm question unless someone else.
Well, I think
I'm wondering about that also.
Yeah.
I think people are ready to move on to midterm questions. For this last bit of time, how much more longer do we have? We got 10 minutes to do all your midterm questions. Cleo.
Did you send an email with the?
I just did at the beginning of office hours because I forgot until then. So you should have the multiple choice sections now. So you can see which ones you got wrong, which ones you got right. What do you want to do on the midterm?
Can we do part C of the written one?
Yes.
Okay.
We kind of need to do part B to do
I
part
was gonna
C.
ask
Okay.
part B.
So let's go ahead and do part B real quick. We're making a buffer at, I have so much of this remembered at this point. We want pH 10 is our target. We want a concentration of, just 0.2?
Yes.
0.2. We want 425 milliliters. And we're using 0.75 molar.
HNO3.
Yeah, I would almost put NaOH. I was like, no, HNO3, right? So, buffer slide. How we're going to make this thing. We are using ethylene diamine, and as you all know, that can also be a metal ligand, right? That's our bidentate metal ligand. It's a chelate. So looking at ethylene diamine, it has 2 KBs associated with it. It's polybasic, which makes sense. That's part of why it acts like a ligand. It can donate electrons in a Lewis definition of a base. We've got KB1, we've got KB2. KB1 is equal to, I need help. I don't have it in front of me.
8.5 times 10 to the minus 5.
And KB2, we don't actually care about. Let's get it anyway.
7.1 times 10 to the minus 8.
Now, we're making a buffer. So what we essentially want to do right away is turn both of these into a pKa1 and a pKa2. If I remember correctly, pKa1 is 9.2 or 9.93, and pKa2 is 7 point something. Doesn't matter, right? So what I want you to realize right now, and I was a little crestfallen because a lot of people got weird answers, and it was like if you just slow down and thought about this logically, you would have been like, oh, my answer is totally wrong. When we look at this, we say, okay, what's my target pH? How close to the first midpoint is that? Really close. A little bit before. So all I need is the volume to the first midpoint, and I have the answer. Approximately. It's about 56 milliliters. It should be less than 56 milliliters would be the midpoint. A little bit less than that would be this target pH. Let's go through and actually do the math to show that, though. So we're making a buffer, so of course we're going to start with Henderson-Hasselbalch. pH equals pKa plus log. I'm just going to call it conjugate base over weak acid because I get to pick how it goes, right? I can think about this as ENH plus going to En plus H3O plus with a Ka associated with a pKa of 9.93, right? And so I'm going to think about it like this. My conjugate base is going to be the ethylene diamine. My weak acid is going to be the protonated form of the ethylene diamine. We're looking at the midterm. So we go ahead, we plug this in. 10 equals 9.93 plus log of conjugate base over weak acid. You're going to get 0.07 equals blah. You're going to get 10 to the power of 0.07 is equal to conjugate base over weak acid. 10 to the power of 0.07 is something like 1.17. Great. Notice if we were exactly at the midpoint, this would just be equal to 1, right? We'd be evenly balanced. We've got something close to 1, a little bit more conjugate base than weak acid because we're a little bit more basic than the midpoint. That's all making sense. We have our second thing that we know. We know that conjugate base plus weak acid equals 0.2. So I can go ahead and do a substitution. I can take this, substitute it in, and I'm going to get 1.17 plus 1 times weak acid equals 0.2. Weak acid is equal to, can I do that in my head, 0.09? 0.0919, 0.092, something like that. That means I can get my conjugate base by plugging it back into this, and it's going to be 0.10. Oh, math in my head. 0.108. Close enough. Right? So this is in molarity because this equation is in molarity. Right? So multiply by 425, it gets you moles of weak acid. Multiply by 425, that gives you moles of conjugate base at equilibrium. This is moles of weak acid. Remember that our weak acid is the ENH plus. It's the ethylene diamine that has been reacted with acid. And our conjugate base is just the amount of ethylene diamine. Notice at equilibrium, at the end of the reaction, not at the start. The problem's asking us for how much at the start. So I know that all of my weak acid comes from ethylene diamine reacting with a strong acid. So this moles of weak acid of ethylene diamine is the moles of strong acid I must need to add. My moles of conjugate base plus my moles, I need this total amount to be the amount I start with. So if I remember correctly, this comes out to be 38 millimoles, something like that. This one comes out to be like 46 millimoles, Something like that. Not doing the math, I'm just trying to remember. Not surprising, we're pretty close to even. A little bit more basic than acidic. pH is a little bit more basic. This all makes sense. I convert the 38, I divide by the 0.75 to get the moles of acid, to get the milliliters of acid I would add. I add these two together and multiply by the molecular weight to get the amount of ethylene diamine I need at the start. I think it's like 5 grams. So the thing that I need is I need the moles here, right? Because we want to get to part C. Notice this is all just the buffers lab. So what I need I need the moles because we want to go into part C. 0.909, I don't remember those numbers. 0.909, sorry, 0.0919 times 425.
Like just the acid and just the base before you like account for the
At the end of the
Oh,
reaction.
sorry.
I just want the end of the reaction because part C works from the buffer that we made. And this is where everybody kind of dropped the ball. Calculators.
Like you want the concentration times the volume?
Yeah.
Okay, for the acid, it's 0.0391, and then for the base, it's 0.0459.
Someone agree with that?
Yeah.
Okay, so now we're going to go on to part B, and I'm going to write the stoichiometry table to explain why everybody dropped the ball. Broke my heart a little bit. Just a little. So when we're doing this, we're now saying, okay, we're in a buffer. I've got my ethylene diamine. I'm adding, let's go ahead and do it as, I've got my protonated ethylene diamine. I'm adding base to it. Essentially, right, I went to pH 10, and then I was like, oh, no, that's too far. I want to bring it back to pH 11. Part C. So right away, I can look at pH 11 and say, is that in the buffer range? No, it's just outside the buffer range. Probably close enough that we can still use X is small, but we shouldn't. Like X is small is probably dangerous to use. But it's outside the buffer range, which means we want this to be almost all in the basic form, not in the acidic form. I can then go ahead and say, okay, I'm then going to have En plus H2O over here. My ENH plus is starting at 0.0391 moles. My En over here is starting at 0.0459 moles. And that is what everybody forgot. Right, I'm going to add some amount of OH minus. That's what we're trying to find. How much OH minus do I add? That's X moles. I'm going to have minus X plus X. 0.0391 minus X, 0.0459 plus X. We then plug this into the Henderson-Hasselbalch. So many of you, not in this room, just in the class, jumped straight to the shortcut and didn't think about the chemistry behind it. And so you didn't get it. If you jumped straight to the shortcut and you didn't do the stoichiometry, I didn't give you very much credit.
So you don't jump to this shortcut because it's not in the buffer range?
No, you don't jump to the shortcut because it's already in the buffer range, right? The shortcut works when we're going to the buffer range, okay, not when we're already in the buffer range. So I'll write the shortcut in red since it's wrong, and then we'll write it in green when it's right. So the shortcut would be pH equals pKa plus log molarity times volume divided by molarity times volume minus molarity times volume, where this is going to be like strong base, strong base, strong base, strong base, weak acid, right? You got your subtraction, but you don't have your addition. You're saying that this is 0. And that's not true. We have to think about the stoichiometry that's actually happening here. So you need to do pH equals pKa. I'm going to label this to be clear. Right? You're just jumping to a shortcut. That's not right. You're not thinking about what you're doing. You're just going, shortcut, great, go. We always have to remember the shortcuts. Always question the shortcuts. pH equals pKa plus log. I'm going to want my conjugate base, 0.0459 plus x, divided by my weak acid, 0.0391 minus x. Solve for x and you're done. Well, solve for x and you're almost done. That gives you the moles and you convert it to molarity by dividing by, it's close enough. If you solve for x and left in moles, I'd probably give you 90% of the credit. Maybe even 95% of the credit because you did all the hard work. Logically, we can think about this logically as well, because some people jump to the shortcut and then they got an answer and the answer just didn't make sense. And I think a lot of people realized the answer didn't make sense, but then they didn't know what to do. If we think about this logically, and I always encourage drawing a titration curve to think about this, right? If we think about this logically, our titration is going to look something like this. We got the second point. We don't even care about the second point. I'll tell you something terrible. I actually made this problem easier than it was supposed to be accidentally. I meant to make a buffer in the second buffer region.
Oh, God. I'm so glad you didn't do that.
So, whoops. So thank goodness. We realized that the first point we were interested in calculating, if this is the midpoint, we realized that the first point, part B, was right there, just a little bit before. And then we realized that part C is over here, like completely outside of the buffer range. We expect that part C is going to be all base, very small amount of acid. That's part of why part D matters. Part D, most people lost credit because they did not recognize the excess small approximation fails because you're outside the buffer region. Lots of people said they make the excess small approximation and it's great. Outside the buffer region, ignoring like that protonated ethylene diamine, the concentration is going to be very low. The excess small approximation is probably going to fail. But in the problem, I said, make the approximations and then we'll discuss whether they're good or bad. What we can realize in this is if you looked at problem C and you went, I have no idea how to do this, but I know how to calculate a buffer at a pH of 11. And you calculated the volume of weak acid to get to a pH level, not strong base, but you did it as if you just did B again, but you did it for the addition of strong acid to a different pH. You'd get just about 5 mils. And so you would get, you could imagine that if it was 51 to get to here, and it's only 5 to get to here, you just want the difference between the two, and that's how much base you need to add to like reverse the addition of the acid. And you get about 45. That's right. If anybody just actually drew the titration curve and said, look, I don't know how to do this, but I know it's really close to the initial pH, so it's only going to be a couple milliliters off, which means I need to effectively add no acid, I would have given half credit. Nobody made the logical argument. Not a single student looked at it and said, let's just look at this logically. Everyone jumps straight to the short, like not everyone, but most people jump straight to the shortcut. And it was one of those situations where the shortcut didn't work. Otherwise, I would just be giving you the same calculation twice and been like, do the same thing twice. And that's not a good thing on a test.
I'm confused why you can't use the shortcut still.
So the shortcut assumes that you're starting with an initial, your base would be initially 0, right? Like this shortcut assumes that you have no ethylene diamine and you're just creating all the ethylene diamine. But we're not. We already have a buffer where there is ethylene diamine. The reason people got nonsense answers when they went straight to the shortcut was because the shortcut says you've got protonated ethylene diamine that you're reacting with a base. But we didn't have any protonated ethylene diamine at the start. So you're also doing something that doesn't make sense. That you were calculating values that were like hundreds of milliliters because they were essentially going from here all the way back. And that's also not what the question was asking.
What was the highest score on this one?
I don't remember. There was somebody who got a 95%. There's somebody who got. The funny thing is, the person who got the 95% did not get 100% on the multiple choice, but there was somebody who got 100% on the multiple choice as well.
Dang.
Ruining the curve. How dare they?
What's that looking like?
Average. Well, a little bit below what I was expecting. I usually expect the class average to be 70%. Right now, the class average is at about a 67%. So it's a little bit lower than I was expecting. But class average is usually about a C+. And it's still within acceptable limits. I do this thing where I really don't like it where people do the standard curve stuff. So I have it where if I wrote the same tests and exams and midterms and everything, and you all were like, we're getting it and we're getting 80% averages, I wouldn't make 80% a C+. I would just give everyone B+. And then next year I'd make the tests harder. Also, if everyone got, like 58%, I wouldn't be like, oh, 58% is a C+. I'd be like, no, you're all getting Ds. I can justify some wiggling of them, but I can't change it that much. Not when I have so much data on how students should perform. It was the first time I taught the class, and I was like, whoa, I just really made that test too hard. Whoops. Because I did that so bad my first time teaching Chem 129. I went from a 2-hour studio class to a 50-minute lecture. You think my tests are too long now? My test was way too long. 20 multiple choice questions, 2 free response. No one got to the second free response. And there was a class that came in after us, so it was only 50 minutes. It was terrible.
So kind of right now, what our grades are, it's pretty much pretty accurate.
Yeah. We can. I'll shut off the camera and I'll take a couple of minutes with anyone who wants to. I can do an approximation. Now that we've got the second midterm out of the way, I can do an approximate calculation. We can look at what you need on the final to maybe get in a range of a certain grade. Any last minute questions? So that was the bulk of the free response question from the exam. Any other questions?
I have a question, but it's not related to this. How many people tend to what?
Someone's watching and has the username Donut and asks for lab final tips. We went over lab final tips at the beginning of the video. Oh, they're not watching anymore. Oh well.
Hello.
Any last questions about the midterm? Let's get out of Dr. Rice's way as well.
No, you guys are good.
Multiple choice questions, any other things? Or
What was just this first part? Just randomly.
you had to write ethylene diamine without the shortcut plus H2O goes to the protonated version. So essentially this reaction backwards without the shortcut twice. Okay, I'm gonna end this and we can do some grade calculations.
How do you